Click the bell icon to get latest videos from Ekeeda.
Hello friends, after numerical number 1, we will proceed further for more complex numerical, that is numerical number 2, which is based on adder circuit using IC 741 as an operational amplifier circuit. Let's see what is given. Here, instead of one operational amplifier, we do have two operational amplifiers. So two-stage amplifier is given. R1, R2 and R1 is given with value 3 kilo ohm. RF is having value 10 kilo ohm. V1, V2, V3 here in this case given as AC signal with peak value 5, 2, 4 respectively. Plus and minus Vsat is given as 14 volts and they ask us to find the expression of VO, that is end voltage we want to find out, and that should be obviously in the form of V1, V2 and V3. Just the difference between the previous numerical and this numerical is here we do have to calculate VO in terms of V1, V2, V3 in the form of particular frequency AC signal. In the previous numerical we have heard about DC signal input. Now we will proceed further with input as AC signal. Now khasiyat of operational amplifier is it can operate with AC as well as DC signal as input. Unlike your BJT and FET transistors, this particular operational amplifier will amplify both AC and DC signals. So that is one of the characteristics of operational amplifier, rather advantage of operational amplifier over your usual BJT and FET transistors ka amplifier. To solve this numerical, we will start from first stage. We will try to get the value of this particular voltage. Let us say that this is VO1, and once we get the value of VO1, proceeding further is very simple as that of previous numerical. Stage number 1 is actually inverting configuration ka amplifier. Here I am treating this as ROM. We don't have to deal with this particular resistance right now for mathematical purpose, and we will calculate the value of VO1. This is your inverting configuration. We will directly write down this VO1 is equal to, how can I find out that particular value of VO1? This is nothing but minus RF upon R1. This value of VO1 we can easily find out as minus RF upon R1 into V1 plus minus RF upon R2 into V2. I am treating this very separately. This is because I know that this V1 and V2 have different value, right? Now we can take this RF common. We will take this as RF minus RF in bracket V1 upon R1 plus V2 upon R2. Very simple. This is usual inverting configuration wala output voltage, that is VO1. Just put the value and get the answer. RF is equal to minus 10K. V1 is of value in the form of sin omega t, AC signal is 5 sin omega t divided by R1 is of 3K plus V2 is of value 2 sin omega t divided by 3K. So 3K and 10K will become 3.33, and ultimately we will be getting the value of VO1 is equal to minus 3.33 multiplied by 5 sine omega t plus 2 sine omega t. We will keep this value as it is because we don't know what is the frequency omega, which is not given, and we can't help with this particular situation. This will be 1 because they ask us to find the expression of VO. Expression of VO means that this will be as it is. We will proceed further for next stage, that is stage number 2. For stage number 2, we will take this VO1 as input for stage number 2. Now this stage number 2 is of differential configuration. This differential configuration gives the value of output voltage in the form of V3 minus VO1. But hold on, here the value of VO1 is expressed as in equation number 1. What we are going to do in this particular numerical, you can also take the help of the formula for differential amplifier configuration wala output voltage ka formula. Otherwise, what we can do, we can apply superposition theorem and we can split up this particular circuit into two parts. One is with inverting configuration and another is with non-inverting configuration. Then clubbed together, we will be getting the value of VO. Okay, so second process we will proceeding further with superposition theorem. By applying superposition theorem, we will take case number A, where we are using VO1 active and V3 inactive. Very simple case. This is VO1 which is active, and V3 which is inactive, that means connected to ground. Whatever output I will be getting, that will be your output of, let's say, VOX. Case number A के लिए VOX. VOX is equal to VO1 multiplied by minus RF upon R1, right? Minus RF upon R1, because this is inverting configuration. We'll make use of the formula of inverting configuration ka gain. I know that what's the value of VO1, we'll put it later on when we'll combine case A and case B. We'll just write the value of RF and R1. What's the value of RF? RF is equal to 10K, R1 is equal to 3K. So this also will become minus of 3.33 into VO1. Let's say equation number 2. Then we will proceed further for case number B, where I am keeping V3 active and VO1 inactive. Very simple case where I am not looking for VO1, we'll keep it as ground. And now we will apply the value V3 to non-inverting terminal such that you will be getting VOY. But here directly VOY we will not be getting. First of all, we will calculate what's the value of VY. That we will be getting by using VDR. So we will say using VDR, we can say Vy is equal to Rf upon R1 plus Rf multiplied by V3. Okay. What's the value of Rf? Rf is equal to 10k. Divide by 3k plus 10k. That is 10 by 13 V3. So I will be getting the value of Vy is equal to 10 by 13 into V3. We will put that value in formula of non-inverting configuration ka gain from we will be getting VOY is equal to 1 plus Rf upon R1 multiplied by Vy. That is coming out to be 1 plus 10 upon 3 multiplied by 10 upon 13 into V3. Cool. We will be getting 4.33 multiplied by 10 by 13. Just check your calci and calculate this particular value. You will be getting the value of VOY in terms of V3 directly. This will come out to be 3.33 into V3 itself. We will treat this as equation number 3. We will club equation number 2 and equation number 3 to get final output. Vox was minus 3.33 into VO1 and VOY is again 3.33 into V3. I will make use of equation number 1. We'll say from equation 1 we get minus 3.33, I will take common, and I will be getting VO1 is nothing but minus 3.33 multiplied by 5 into sine of omega t plus 2 sine of omega t, bracket completed. This whole and soul, this completely the value of VO1. So first part is completed, minus 3.33 into VO1. We will complete this part and then we will proceed further for plus 3.33 multiplied by V3. What's the value of V3 given? V3 is equal to 4 sine omega t. So we will write this as 4 sine of omega t. Now if you combine this all together, we will be getting something in the form of sine t, a sine omega t plus b sine omega t plus c sine omega t, such that I will be getting a plus b plus c sine of omega t. 3.33 multiplied by 3.33, minus minus will get cancelled, and altogether we will be getting completely addition. This we will be getting 55.44 sin omega t. Then we will be getting minus 3.33 minus 3.33 multiplied by 2. And plus 3.33 multiplied by 4. And just calculate these three terms, you will be getting something in the form of sine of omega t as your output voltage. Now question arises, this answer is in volts. Now question arises that do we have this kind of value 90.94, which is practically possible if saturation voltage is well below 15 volts, that is given as 14 volts plus or minus 14 volt, which is nothing but your saturation voltage, and beyond saturation voltage I will not get the output in terms of your AC or DC signal. That means here somewhere in the form of AC signal I will get clipping well above the 14 volts, right? So we have to write the comment in your answer itself. Your waveform will get clipped off and we will not get proper amplification. In the question itself they may ask you that whether it is possible to get the amplification in this particular circuit, yes or no. So your answer is no. This is because we will not get full swing, we'll get the clipped waveform. So your practical answer should be 14 sin omega t, because your value will not reach beyond 14 volts. Peak value will not reach beyond 14 volts, and that is why we will be getting the value VO is equal to 14 sin of omega t. Rather, waveform will get clipped off above 14 volts as plus minus Vsat is equal to 14 volts, right? So to get 90.94 sin omega t at the output voltage is next to impossible. So we will be getting the value VO is not properly amplified voltage. As far as mathematics is concerned, we can easily get the value 90.94 as a correct value, but practically it is not possible. So what will be remedy for that? We have to change your input voltage, or we have to design your circuit such that we will be getting the value VO well below the value of 14 volts. I hope you clearly understood the conceptual and mathematical terms in the form of adder and subtractor circuit with two-stage circuit in this particular numerical. I hope you like this particular video. If you like it, like, share and subscribe this particular video. Subscribe Ekeeda channel. Thank you so much.